And okay, I'm hoping that we can see the PowerPoint slides.
Yeah. Yes.
Okay, very good. So I'm going to start here. I know that we've already been through this, but I want to sort of make sure that everybody understands what's going on here. Okay, what we learned on Wednesday is that we can have a population, all right, and that population could have a population mean, and that population mean is symbolized by mu, and that's pretty straightforward. But we also can have a sort of an idea of the average of the means, okay? So this would be if we had all the combinations of a population and we sort of went out and started to do sampling distributions, we probably could see that the average of the sample means, is going to give us a very good idea of what the population mean is. All right, and in this same sort of idea, sample size is important. Okay, sample size is important. Sample size is important because as the sample size gets larger, okay, the variation of the average of the sample means, the standard deviation of those sample means will go down. Sample size goes up and the variability goes down. Let's see here. What's this? Okay, sir. Okay. Let's back up. Okay, 1 second, please. What's up here? Okay. So what we learned here is rule number 1, the average of the sample means is going to give us a very good estimate, if not a very accurate measurement of the population mean. Okay, rule number 2, the standard deviation of the sample means is going to be equal to sigma, which is the population standard deviation, over the square root of the sample size. So here, right here, tells us why we would expect as the sigma goes up, as the sample size goes up, the standard deviation of the sample means will go down. As this gets larger, this is going to get smaller. Questions about that? And we can call this number right here, this equation right here, sigma over the square root of the sample size is the standard error. Now, while we're thinking about these ideas about the population and the 10% here, we want a large population so that we can have a reasonable sample size. Okay, so we don't want the sample size so large that it's basically it's got to be lesser than 10% of the population. Okay, so this too was something that we went through, and we said that this is a normal distribution. It's a bell-shaped curve. In this particular situation, the mean is at the center, which is 8.25, and the standard deviation of that population is going to be 0.75. And that's what this sense is saying right here. Here's the center, and the standard deviation is going with 1 standard deviation above the mean. Okay. So what we're going to do is we're going to start out with 500 random samples. And for each sample, okay, we're going to have an N of 5. And then we're going to compute the sample mean of each one of the 500 random samples. All right, and we're going to do this with a sample size of 5, 10, 20, and 30. All right, and I understand we have already gone through this, but I wanted to go back and make sure that everybody got a second look. Okay, so here is the 4 different histograms that give us an idea of the effect of the sample size. And what I'm trying to do here is I want you to understand that this here, the x axis, is sort of, it's the same here as it is right here, okay? So n equals 5 and n equals 10 have the same scale on the x-axis, all right? And you can see that this here is more narrow, okay, more narrow than this one here, suggesting that a sample size going from 5 to 10 will reduce the variability, right? Now, also understand, okay, that these values right here on the x-axis shows the effect of the sample size in terms of the standard error, okay? These are values that go along with, or the variation is going along with the standard error. Now, in these bottom 2 histograms, the scale is somewhat changed, okay? And it's not going from, it's going from 7.2, but it doesn't go all the way to 9.2. So we're thinking about this idea of going 20 and a sample size of 20 to 30, and we start to see that the that the distribution is very narrow, it's symmetrical, and again, it's very narrow too, due to the size of the sample. All right, and this is where we left off. If the population standard deviation is normal, then the sampling distribution will be normal no matter what the sample size is there. Okay, so here is new material, and we're talking about a sort of an idea of the time of minutes from the start to the game and the first goal scored in 281 regular season games in the NHL, hockey. Okay, we're talking about hockey. And we have a sample size, a population sample size of 281 games. And it's the time of the first goal. So here is the distribution, okay? And here is the x-axis, the time in minutes from the first goal. Now, we see that this is strongly positively skewed, okay? So there's a great deal of skew here, and we can say that the the population mean is 13, right about here, and the median is going to be inside of the mean, and that's at 10 minutes. So here is a situation where the population distribution is very skewed. The population is very skewed. This is different than the previous example, where the population was normally distributed. This has a great deal of skewness. So what we want to start to think about, does the things that we saw with a population that is normal, is that going to show up when we have a skewed distribution? All right, so let's start thinking about this. So we'll do the same sort of thing that we did with the previous example. We'll take 500 samples, okay? 500 samples and a sample size of 5, 10, 20, and 30. All right, so we're going to, for example, we're going to take a sample size of 30 out of 281, and we're going to do that 500 times, okay? And then we're going to determine the mean and the standard deviation of those values. Questions about this? Excuse me. All right, so let's see the 4 different histograms, okay? And again, what we're thinking, all right, here is sample size of 5, 10, 20, and 30. Let's start with 5 first. What do you see about this distribution that would be notable?
So that like around 8 is like a high density.
Okay.
Let's do
Uh, so where do you think, Eric, where do you think the mean is?
I would say the mean is probably like 12, like around 12.
Okay. And just to go ahead and say, the mean here is about 13, right, Eric?
Yeah.
Okay. And if we go back, I'm sorry, if we go, come on, come on, come on. If we go to this one here, it's probably the center is pretty close around 12 or maybe 13, something like that. Is it symmetrical?
Not really, I think.
Okay.
Like it's a bit more skewed on the right, I think.
Okay, so it has the remnants of the population mean, of the population distribution, right? Where it's sort of very kind of skewed. And you sort of see that same skewness in the histogram that's going along with a sample size of 10. Still has some sort of remnants of that skewness that was shown in the population distribution. Okay, so at 20, you still see a hint of it, but by 30, you're certainly seeing a symmetrical distribution. Would you agree?
Yes.
Okay. So this is quite remarkable, for example, that this population distribution could be seen as symmetrical at around a sample size of 30. Okay. We do see sort of the same sort of idea that the sample size of 5 is going to have a lot of variability, and 10, 20, the variability starts to shrink, and by 30, the distribution is very close to the center of the distribution, and it looks like it's bell-shaped and symmetrical. Questions about this? Okay. So it looks like each histogram is centered around mu equals 13, and that's here, here, and here is very easy to see. The standard deviation of these histograms are lesser than, okay? They are decreasing as the sample size is increasing. And the shape of the curve is influenced also, I think, by this sample size, this being very symmetrical, this being very affected by the population distribution. Okay, so here's rule number 4, and this is the central limit theorem. Okay, the central limit theorem is a very, very core theorem that really got statistics off to its own discipline. The central limit theorem. So when n is sufficiently large, okay, the sampling distribution of the sample means will approximate a normal curve, okay, even if the population is not itself normal. Okay, so we had a very skewed population, but by 30, by a sample size of 30, it was very similar to a normal curve. And this gives you the sense of what's going on here. Here is the population, which is skewed with a small sample size. It too will be skewed, but by around 20 or 30, we get a nice, narrow, symmetrical distribution. Questions about that? So how large is sufficiently large anyway? Well, if we went to go back to this picture here, I would suggest to you that sufficiently large is n equals 30. Okay, this here has a hint of it. The here is also skewed, and of course the first one is very like the population distribution. So I would say it was how sufficiently large? I would say n equals 30. All right, so the central limit theorem can safely be applied if n exceeds 30, often called the 30 rule. All right. So let's try to think about this example here. So we have a soft drink bottling manufacturer, and of course the average cans contain 12 ounces of soda. All right, so X is denoted, and we're looking at each of the soda cans, and we're going to actually test the volume and start to think about randomly selecting cans off the assembly line. Okay, so we think that the population mean is 12. We think that the standard deviation is going to be 0.16, and we're going to have a sample size of 16 cans randomly selected, right? So X is the resulting sample mean for the soda. All right, so if we were to start down this road, if the claim is correct, then the sampling distribution of X bar is normally distributed with mu being 12, and the standard deviation, okay, of the sample means will be 0.04. Now, here is the, just to give you a sense, so this number right up here, sigma equals 0.16, is the population standard deviation. This term right here is derived by the population standard deviation, and it is actually the standard deviation of the sample means. So that's something that is used. Here is sigma, and here is the square root of n, which is 16 cans. Questions? Okay, so what is the probability that a sample mean soda volume is between 11.96 ounces and 12.08 0.8 ounces. Now, when we're getting down to sort of ounces that go into double digits or double decimal places, those are very small volumes. All right. So here is a normal distribution. All right. Right here is a normal distribution. And the center of that distribution is right at 12. All right. So don't let your eye fool you. This is actually normal. And the center of it is 12. All right, so how would we go about understanding what the area under this curve is in blue? How would we do that? Well, I did it this morning, and what I would do is I would get my calculator out and I would go to second vars, go down to normal CDF, and fill out the distances that go along with this. All right, so we could put this in the low column. This is the upper value. We have a mu of 12, okay? And we have a standard deviation of 0.04, okay? That's what you have to use if you're interested in getting the area under the curve. You have to use this value right here, not 0.16, but 0.04 to find the area under the curve. All right, so here is the z-scores that we want. We're going to use a sample mean here, and we're going to use the sample, mu for x sub r, so that's going to be the same as the population mean. And we're going to start to think about this standard error as the denominator. And if we did that for this one, so the z-score for this variable, this value right here is -1. Z-score for this value right here is 2. So the area inside of the blue shaded limits, all right, would give us a value of this here is, this one goes along with this one here, and this here is at this one there, and the probability then is 0.8185 inside the limits that are shown here. Questions about that? Okay. All right, so here is another example. Okay, we're talking about a hot dog manufacturer. Okay, and the manufacturer wants to let consumers know that the average fat content of 18 grams per hot dog, boy, that sounds like a lot of grams, with a standard deviation of 1 gram. Okay, so for those people that are consumers, they wouldn't mind having lesser than 18 grams, and probably would be unhappy if it was exceeding those limits. So the manufacturer got a team of statistics and started to think about a random sample of 36. And the result of the sample means were 18.4. All right. Does this result suggest that the manufacturer's claim is incorrect? Okay, so what's good about 36 here?
It is greater than the 30, so it fits with the 30 rule.
That's exactly right. Okay, so we feel really confident with this random sample because it's over the limit of 30, sample size of 30. Okay, and of course, if the sample mean here, the mean of the sample means is going to be 8.4, that sounds like that might be a little high. So let's go ahead and start working with this problem. So since the sample size is greater than 30, it follows the central limit theorem. All right. So here is the outcome. This is the distribution of sample means, the average of the sample means. This is this one here is the one up here that is the standard deviation of the population. 36 is the sample size, and then this then is the sample, the standard deviation of the sampling distribution of 0.1667. Okay, so what would we do? Does this result suggest that the manufacturer's claim is incorrect? So we want a probability that is greater than what we saw with the sampling distribution. Okay, here is the mean of the sampling distribution. So if we got the sampling distribution, the mean of the sampling distribution minus the population mean, okay, and here is the standard error, this z-score would be 2.40. What do you think about 2.40? Is that a large or is that a small z-score?
Pretty large.
Pretty large, I would agree, okay? It's really out there on the right tail, and it's probably pretty large. So the probability of that, okay, the probability of that 0.008 is very, very small. This is a probability that goes along with this z-score. So that would be suggestive of that is very unlikely in the right tail. All right, so values of the sample mean at least as large as 18.4, that is observed 0.82% of the time. And that is a very, very small percentage. So the sample mean of 18.4 is large enough to cause the consumer to doubt the manufacturer's claim and be worried about the increased fat in the hot dogs. Okay. So questions about this? All right. So let's start thinking about one other thing that we can start to pick at. Now, we've been talking about sample means, okay? And those are different than sample proportions, right? So P hat right here is a sample proportion. This hat right here, P hat, is another statistic, okay? So we can have X bar, we can have P hat, and both of those are statistics. We've talked a lot about the sample mean, and now we're changing our focus to the sample proportion. All right. So P hat is also a statistic. All right. So say, for example, we toss a penny 20 times and record the number of heads. All right. Calculate the proportion of heads and mark it on a dot plot on the board. What would be the shape of the dot plot? So we're going to do, what we would do is take a penny, flip it 20 times, and it's record the number of heads. And we would do this over and over and over again, maybe 500 times. So we would build a dot plot and understand what the shape of the dot plot should be. All right. So we have a sample size of 20, and we're going to create a sampling distribution with that shows the dot plot. All right. So what would happen to the dot plot if the flipped coin goes from 20 times to 50 times? What's going to happen to that distribution?
Would it be, since we're increasing the sample size, that the variability would decrease?
That's right. And what we saw with the sample mean occurs with the sample proportions. Okay, so the distribution will get smaller in terms of its variability. Okay, so here is homework for the weekend. Okay, got a few problems here. I have set up these problems so that you can read the chapter, and it's you know, it's a pretty dense chapter. It's not really all that long, and here are some problems on different parts of the chapter. And so I'm thinking that we want to have this done by Wednesday. next week. All right, Wednesday next week. So it's due on Wednesday. And so it's part of the PowerPoint that I will put up on Moodle. I put this homework assignment in the set, not knowing where we would get to on this session. But let's keep on going with some lecture notes, and we'll start to think about proportions. Okay, questions about this? Okay, we still have a few minutes, so let me get a few more slides in here. Okay, now I have a typo here. All right, these problems right here, it's not 8.1, it's 8.10. Okay, sorry about that. Does everybody hear that?
Mm-hmm.
Yeah.
Right? This is a typo right here. It's supposed to be 8.10. Okay. I'll fix that before I post the PowerPoints. Okay, so let's get into it, right? Sampling distribution for a proportion, a sample proportion, okay, P hat. Okay. So remember, we have been introduced this problem, okay? So P actually represents the population proportion. And P hat is the statistic that goes along with that. So here is the parameter for a population proportion, and here is the statistic for the sample proportion. So try to keep this notation, clear. Okay. So the distribution would be formed by a sample statistic. Every possible different sample will give a given size for the population. All right, so P hat is the number of successes that go along with the sample. Number of successes. All right, so here is a population of 6 students. It's kind of hard to actually call that a population, but okay. And so there are 4 guys and 2 gals. All right, of course, it's a very small population, but we want to do it so that we can see all the different possibilities in very small sample sizes. Okay, so we're interested in the proportion of females in this population of 6 students. All right, we want to know the parameter of interest, okay? We want to know the proportion of females. All right, the proportion is 1 out of 3. 2 over 6 is equal to 1 out of 3. All right, so let's take a look at these possibilities, and we want to think about how many different samples could be possible with given the sample size or the population size is 6 and the sample is 2. All right, and that is a combination of 6 possibilities and 2 selected, which is equal to 15. All right, and these are all the possibilities that go along with this. Okay. So obviously, Alice and Denise will give us 1, okay, right? And Alice and Ben will give us a proportion of females 0.5. Ben and Charles don't have any females in that sample, so that's 0. And that's how you would read these types of numbers, okay? So we want to find the mean and the standard deviation of these sample proportions. So what would you do? You would take all of these numbers, 15 numbers, add them up, and divide by 15. All right? And that would be the average, the mean. And you would do the same thing with the standard deviation, all right? And that's how you would get these values. All right, and so the population, the mu is for sub p hat is 1/3. And the standard deviation of the proportions are 2.98. 0.298. Okay, so we can call these means. Okay, we can call these means because we're using the values of the proportion, and it would be sort of a mean proportion. Okay, same thing for the standard deviation. So I think I'm going to stop right here, and we can pick it up again on Wednesday. Okay, let's use Monday as a homework day, and let's get the homework done by Wednesday. If you have problems along the way, please email me. I would be happy to help you out with some of this. It's a little bit dense, and but it's real statistics. Okay. Questions? Okay, if there aren't any questions, I'm going to turn off the recording, and I'll bid you a good day and a good weekend.
Thank you, you too.
Thank you.
Thank you.
Thank you.